to it. That's never happened before. Like I said, this week's lecture focused on transition metal catalyzed cross-coupling reactions. And so that's what we're going to focus on in this kind of mini review session. And so the first thing that we have to do when thinking about transition metal cross-coupling reactions is learn how to understand the oxidation states of transition metals. This is something I think is covered in intro organic chemistry or intro chemistry classes, but I want to go over it again and make sure that we all feel really comfortable assigning oxidation states and get lots of practice at it. And just for a general disclaimer, in this class we talked a lot. We've talked a lot about oxidation level, right? We use oxidation level as a formalism for discussing oxidation and reduction reactions of organic molecules. But I want to remind you all that oxidation state is not the same thing as oxidation level. Oxidation state is a formalism we mostly use for transition metals. It can be used for basically everything, but it's mostly used for transition metals. And oxidation level is a different formalism that we used for thinking about oxidation and reduction reactions. These are not the same thing. They can be correlated, but don't confuse yourself with them. They're just different. Oxidation state, different than oxidation level. Okay, and so what we learned in class yesterday is how to count oxidation states. For example, we have this palladium complex shown here. It consists of the transition metal itself, palladium, and 4 ligands, or really 2 ligands that are bidentate, that bind twice. The main way we count oxidation state is to dissociate the ligands. Imagine the electrons from the ligand palladium bond going back to the ligand, and now analyze the complex in this bond broken form. And in this case, we see for all of these phosphine ligands, we dissociate them back and they gain their lone pair back. But we know, of course, if we were to assign formal charges to these phosphorus to phosphorus here, we know it does not have a formal charge, and you can think about that as it has a formal charge similar to nitrogen, right? It's like how you count nitrogen. Phosphorus, it has a formal charge of 0 when it is making 3 bonds to something else and has a lone pair, right? No formal charges means this is completely neutral, and so there's also no formal charge on palladium, and so this is a palladium 0 complex. Alternatively, you can have for this palladium chloride complex, if we imagine breaking the bonds and giving electrons back to chlorine here instead, we notice that the phosphines are still neutral, but in this case we've got a chloride anion, right? It's chlorine with 8 electrons, which is a formal charge of -1. And since we were able to make a chloride anion, we have 2 negative formal charges, and so palladium must carry an oxidation state of 2+. And so this is a palladium 2 complex. I hope that you see that this is pretty, I think, once you get used to doing this, is pretty routine. All you have to do is dissociate the electrons toward the ligand and see if it's negative or neutral or positive. In the case of things we'll cover in this class, you never have to deal with positive ligands. So here are some complexes that I have drawn out for you that I think you should take the next 5 or so minutes to practice counting oxidation state on. And so we'll discuss this in just a couple of minutes. Okay. Okay, do we feel good about this, or do we want to take a few more minutes to practice these? You can just put a yes or no in the participants window or say so in the chat. Yes is we feel good, by the way. Great, we feel good about this. Good, I think this is something as we practice, we should become very routine, as I said. So let's just go through these really quickly. For just to reiterate what we want to do here, the way you think about this is you dissociate the electrons back to the ligand, and if you look at the formal charge of the ligand, and if it has a formal charge of -1, then you go up one oxidation state. And so we see here for this titanium complex that if you dissociate each of these ligands, you get the chloride anion, or in this case, in the case of the methyl ligands, you get the methyl anion, which is, so it contributes also to the oxidation state. And so here, the oxidation state of titanium should be 4 or 4 plus. Okay, and now for this nickel complex, we know that the phosphine ligand, since when we dissociate it, it gets back its lone pair, it has a formal charge of 0. It does not contribute to an oxidation state, and so we have 2 ligands that do, and so this is an oxidation state of 2 plus. For imine ligands, it's the same way. You dissociate this back, nitrogen gets back its lone pair, and therefore it's a neutral ligand. Oops, it's a neutral ligand, and so this is a cobalt 0 complex. Amino ligands, not just imine ligands, also can get their lone pair back, and so this is a nickel 1 complex. Diethyl zinc here, these are 2 ligands that dissociate as anions, and so this is zinc 2. Acetate ligands are formally, so if we dissociate both bonds of these ligands, we see that what we get back is acetate. Right, so in this way, it's not only a neutral ligand, but also an anionic ligand, so it counts as one of each, and so therefore, this is a palladium 2 complex, because it has 2 anionic ligands. This here has 4 ligands that we can now dissociate anionically, and so this is a palladium 4 complex. Palladium 4 complexes are pretty rare, but they do exist, maybe. Depends on who you ask, but we're pretty sure they exist. And then this is the phosphine ligands dissociate as neutral. And of course, if you bring electrons back to hydride, you get H minus, which makes this a cobalt 1 complex. Any questions on this? Like I said, this should become, as we practice this, it should become pretty quick for us, and really should be pretty straightforward. But if you have any questions, let's iron them out right now. Okay, no questions. We're going to move on to relecturing the material from yesterday in the form of the elementary steps of cross-coupling processes. And so we learned the elementary steps yesterday, and I just want to take a brief reminder of each of them and try and explain them in maybe a different way than Felix did, so they really stick with us. And so the first of the elementary steps for transition metal processes is oxidative addition. This is the formal insertion of the metal into a bond, increasing the oxidation state of the metal by 2. we should all have been familiar with processes that look like oxidative addition from our use of Grignard reagents. This is a mechanism might be a little bit different here, but formally it's very much the same process, right? We take an aryl bromide, treat it with magnesium, and we form these Grignard reagents wherein magnesium has inserted itself into the carbon-bromine bond. And so if we were to assign an oxidation state to magnesium, it would be 2+. So we're already very familiar with oxidative addition processes. We're just now going to apply them in a more general fashion. And so the way this often looks is that palladium 0 can insert into an aryl halide bond to make a palladium 2 species. Aryl halides here are chloride, bromide, iodide, or a pseudohalide as a triflate. Fluoride is not very good for oxidative addition. In fact, the rates of oxidative addition we discussed yesterday is iodide, then bromide. I feel like I did not mention this in last year, but bromide is around equal to triflate, which is faster than chloride, a lot faster than chloride, which is way, 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 way faster than fluoride, right? And so we can predict the rates of oxidative addition based on these things. This is due to the weakening of the bond, or sorry, the fluoride has a stronger bond than iodine. And so this series follows bond strengths pretty closely. It's not just palladium 0 to 2. We can also imagine having a nickel 1 species that can oxidatively add into nickel 3. So it's not just 0, 2, it can be 1, 3, it can be 2, 4. It just is an oxidation state of change of 2. The next of the transition metal elementary steps is transmetallation. And this is, oh, just real quick, does anyone have any questions on oxidative addition? Okay, no questions. Transmetallation is the next of the elementary steps. It is the exchange of a ligand from one metal to another, and it does not change oxidation state. This is a redox neutral step. And so in general, this looks like and for the purpose of the class, is going to be one metal. It's normally palladium, nickel, or copper in the case of this, of what we'll be talking about in this course, that can react with another metal, metal prime here, make the prime even bigger. And this is normally boron, tin, magnesium, copper. And we'll talk about the specific variants of each cross-coupling that uses each of these different metals. Throughout in probably the next lecture and maybe the one after that. And so all of these reactions are quite useful and their mechanisms are important, and we'll talk about each of them in turn. We've talked about boron in class so far. And so a classic example of this is you could have a palladium 2 oxidative addition complex like this that can transmetallate to a boronic acid of interest to give this palladium 2 biaryl complex, as well as we see that the iodine got exchanged for the aryl group. And so this is just a ligand metal to metal ligand exchange. Pretty fairly straightforward. The exact mechanism is depends on the metal and depends on a lot of conditions. We're not going to discuss it in detail. I think that's true actually for oxidative addition as well. These elementary steps are less definitive mechanisms as they are processes. And so we don't draw arrows for them because it's formalism not to, and two, because for all these various processes, the oxidative addition can proceed through various different mechanisms, as well as can transmetallation. And so these are just elementary steps of a process. They don't describe the mechanism for sure. And the third elementary step we have is reductive elimination. And this is the formation of a bond between two of the ligands, and it reduces the oxidation state of the transition metal by 2. And so very generically, this process looks like this, where you couple together 2 of your ligands for reduction in oxidation state of 2, and gives you the coupled product. And so for that palladium bi-aryl complex that we just showed, it can reductively eliminate from palladium 2 to palladium 0 to give you bi-aryl. We also had that a nickel complex earlier, so this is nickel 3, and it can reductively eliminate to give nickel 1 and a bi-aryl. So the important things here is that this is normally the last step, the terminating step of our catalytic cycle of these cross-coupling processes, and the bond-forming step, and they result in the change in oxidation state from 3 to 1. I think we just pretty quickly went through all 3 of the elementary steps that we've discussed so far, but I think that they're important to know, but I think they follow pretty directly from observation or from learning them. So I'm really happy to take any questions you have on this. If not, we can move on to an application of this reaction that we learned in class. Okay. So one of the major and one of the most noteworthy reactions, I think, of the 20th century is the Suzuki reaction. It won a Nobel Prize, as well as many of the other cross-coupling reactions that we're going to learn later in the class in 2010. Suzuki won it, as well as many other chemists, for the contributions to transition metal catalyzed cross-coupling processes, which are just by far, in a way, maybe the most useful chemical reactions at least in the pharmaceutical industry, but as well as in many other chemical industries, for the ability to really build molecular complexity in a mild as well as selective and controllable fashion. So these have really revolutionized the way we do chemistry. And so the Suzuki reaction typically is the coupling of an aryl halide. Here I've chosen an aryl iodide and an aryl boronic acid. It can also be a boronic ester, which would be something like this is an aryl boronic ester. This group here is typically abbreviated as PIN for pinacolado. So this is a B-PIN ester. So the Suzuki reaction uses a palladium 0 catalyst normally, a base of some sort. Typically it's a hydroxide base, but it can be others, and it can be run in ethereal or aqueous solvents. And it gives the cross-coupled product, wherein we're forming a bond between this carbon and this carbon. And so the way this process works is you have your palladium 0 species. Right now we have palladium 4, palladium with 4 triphenylphosphine ligands bound. This is not the active catalytic species. Palladium 0 sits as a square planar complex. So all these bond angles are 90 degrees. And with 4 triphenylphosphine ligands bound, it cannot do oxidative addition. It's too hindered, and it needs open coordination sites in order to do that. And so an equilibrium process occurs where palladium starts to shed some of these ligands. So you have 3. Or 2. Now that we have this, we have some open coordination sites. These are free to bind something or to have our oxidative addition complex. This can also undergo another equilibrium to lose another triphenylphosphine ligand. There are some Suzuki processes where it has been shown that this monoligated palladium species is the active catalyst. There are some where it's where there's where you have two triphenylphosphines on, but the general theory here is we lose some of our triphenylphosphine ligands in order to make an active catalyst species that either has 2 or 1 of them on there. This can undergo the oxidative addition elementary step to give us this oxidative addition complex shown here. This is now palladium 2. This transmetallates with our boronic acid of interest. Notably that under aqueous basic conditions, the boronic acid could exist as the boronic acid or as the boronate, wherein sodium hydroxide attacks the boron species. It's been shown that these boronates are a little more active in this transmetallation process. And so it's most commonly that these are the active species for transmetallation right here. But you can also do it with boronic acids. It's just a little bit slower. That gives you the byproduct from transmetallation where you have the iodide borane, iodide boronic acid or iodine boronate. The iodine can then get displaced by your aqueous base as well. And now you have your palladium 2 biaryl. This can undergo a reductive elimination to regenerate palladium 0 and our biaryl product. This is, really groundbreaking chemistry, and we're going to explore it a lot more in this class. But that really covers the extent of what we really talked about in class, minus one last part, which is the preparation of boronic acids that we'll cover in a practice problem. Does anyone have any questions on the Suzuki reaction? We're going to cover a lot more transition metal catalyzed cross-coupling reactions, but we've just touched on this one today, yesterday in class, and so there's more to come on this. But I think probably follows. So any questions? Okay, we'll do a practice problem. Okay, synthesize this guy from benzene. I'll give you 8 minutes. Okay, so we've had a little time to think about it. Does anyone want to propose an answer? Obviously, this is going to use some of our new knowledge with the Suzuki reaction. And so I'll simplify this in that I think that the best answers go through um, forming this bond last using a Suzuki reaction to make from either this coupling partner and a coupling partner like this, or the iodide and boronic acid are switched around. So does anyone want to give an answer for this? Okay, well, it seems like not. So I think you'll also, the strategic thinking that I have here is that the aryl-aryl bond can be made through the Suzuki reaction, right? And so that breaks us down to two simpler building blocks for us to figure out how to make. And so, like I said, you could make this building block, or it could be an iodine here or halogen here, and you can make this building block with the similar constraints. And so let's focus on making this one first. And so the way I would make this is take benzene and do a Friedel-Crafts acylation. Right? We note that these two positions are meta-related, so I want to introduce a meta-director into our ring to give us and we know we can reduce the acyl group and switch its directing capability. And so we want to make a compound that looks like this. And then I'm going to brominate. We learned at the end of the class a couple of ways of turning halogens into boronic acids. And so my goal here will be to introduce a bromine that we can change into our boronic acid. We're going to learn some other ways to introduce boronic acids, but one of the great ways is always through a halide. And so now I'm gonna go ahead and reduce my acyl group, which we can do a Wolff-Kishner reduction for. That puts in our ethyl group. And now we can treat this compound with magnesium to form a Grignard reagent. And then react the Grignard reagent with a borane species. That gives you the borane, or actually this is a boronate ester, I apologize. Just imagine the Grignard displacing one of the methoxy groups. This is 2. Which can be hydrolyzed on workup to give us a coupling partner A. Does that make sense to everyone? Any questions on this sequence for making A? Just using some of the chemistry that we've learned in this class before, we recognize the meta relationship, we put in a meta director, and then reduce it to the ethyl group, and then can make boronic acids from Grignard reagents. And so that's, I think, a good way to make A. And so we'll call this B. And so how we make B? So to me, when I look at B, I say, okay, well, I see the nitro group and the iodine are orthopara to the bromine, which is an orthopara director. So we could think about introducing the iodine and then the nitro group is a good way to do it. Or we could introduce the iodine, or we could introduce the nitro group, then the iodine, and then the bromide. I think either of those sequences is fine. So we just can bromine, or we can iodinate here. You can use iodine, and you can use like an iron halide. People will oftentimes use iron tribromide, but we can think, I don't know if iron triiodide is very synthetically usable, but let's pretend, or let's just go ahead and use that. But I do think you can use iron tribromide here. Puts in our iodine. Oops, we don't actually want to do that yet. First, we want to put in our bromide. So bromide. Then we can iodinate. Ooh.
Why does the order matter?
Oh, well, I guess it doesn't. And then you nitrate last. So so sorry, when I was thinking about this, I was thinking that this nitration might be a little tricky to get selectivity over this position versus this position. But bromine's smaller, so you might get nitration selectivity where you want it to. I think a more selective synthesis would look like this. The more selective synthesis is the other one I was discussing. But I think both are probably acceptable. Where you nitrate first, then iodinate. This will go selectively meta, and then brominate. Now you have a little bit of trouble between ortho and para, but you'll get a good amount to go para. And so I think this top one is more selective, but both are probably okay. And then we can take A plus B and react with a palladium 0. If you're, I would say for when doing synthesis problems, your go-to palladium 0 source should be palladium tetrachus, which is palladium with 4 triphenylphosphines, sodium hydroxide. It's a great base for Suzuki reactions. THF water is one of the ways we'll always start, and that'll give you a product. The selectivity here is going to be that oxidative addition is favored into the aryl iodide bond, preferentially over the aryl bromide bond. And so that's how we get the selective cross-coupling here. So I think this is an example problem that shows the utility of the Suzuki cross-coupling reaction, as well as we now know that we can make boronic acids and boronic esters from halide equivalents. And so I think those are two really important things that came out of yesterday's lecture. And as we develop more of this chemistry, we'll get into doing some more nuanced problems. But I think for now, this is all we've had based on one lecture's worth of material. And I'm done lecturing, but I'm happy to take any questions anybody has on this or any other material. Any questions? I hope everybody's doing okay. It's a, and I'm still in, and I don't know if how many of you are still in Berkeley or not. I'm still in Berkeley. It's the shelter in place has been fun, like not fun, but like it's a weird situation. So I hope everyone's doing okay, and I hope you all had a nice inside spring break and are now getting back to doing your online classes and are doing okay in general. It's a pretty challenging time for all of us, and I know it is really disruptive to your time as a college student, and for that I'm really sorry, and hope that we can all just get through this together. But yeah, any other questions you guys want? Yeah, we'll hopefully just keep doing these meetings every week and having some fun doing problems and get back to it. Yep. Yeah. All right. So if there's no questions, I hope you all have a really good week, and I'll see you next week. Oh, a quick question about the solvent for chemoselectivity lab. DMSO. So the NMR solvent is going to depend actually on the substrate you're using. For the substrates that are very polar, like the ones that make carboxylic acids, you'll need to use DMSO. For the less polar substrates, you can use deuterated chloroform. This is just a solubility thing. Your GSI should handle that. Oh, I guess you guys aren't actually doing it. Holy crap. Yeah, so it depends on the substrate. I don't remember entirely, but for like the ones that had like carboxylic acids, you do use DMSO. For the ones that are just alkyl groups and stuff, you do CDS. You use deuterated chloroform. Yeah. Yeah, Julia, that's correct. Yep, the coupling partners could be inverted if you'd like. That answer your question, Erica? Yes, kind of. Yeah. Yeah, I since I'm not doing the lab stuff, I don't know exactly what the assignment entails, but yeah, maybe you can follow up with your GSI, or if I can pull up the lab files and see and we can talk about which substrate you had. So when we're assigning, we just have to guess which solvent is used. So you should be able to tell. And it, or in most spectra, it says at the top left corner what solvent was used. But if you can't, if you don't see that, then for chloroform, you should be looking for a peak at a singlet at 7.26. ppm, and I don't recall the DMSO one off the top of my head, but it's like 2 point something, I think. Yeah. Okay. Have a great week.